Hi, in this session we're going to be looking at this comprehensive problem. We're determining the rate law for this hypothetical reaction. So we have to write down this rate law. Remember, the rate law is this mathematical expression that relates the rate of my reaction with the concentration of each of the reactants participating in the reaction. So we have to determine the partial rate orders for each of them that are represented by these exponents alpha, beta, and gamma in the equation. Now, the method of initial rates consists on developing a series of experiments in which I change the initial conditions of concentrations, in this case for my reactants A, B, and C, and I measure how the initial rate changes accordingly. Now, the method that we're going to be using, the approach to solve this problem, is to look at the data that we have, and we're going to be trying to find experiments in which I keep the concentration of some of those constant while changing only one of them. Why we're doing this? Because that way we're going to be looking at any changes on that we observe on the initial rates are only due to the changing concentration. The other ones are kept constant, so it doesn't have an influence on the rate. So at the end, I will be able to write down the rate law with the right numbers for the partial rate orders for my components, alpha, beta, and gamma. Now, during a class, we did some examples in which this relationship was relatively easy to catch by inspection, but I show you this one expression, general way to find out the partial rate order. I'm going to ask you to use it for all the problems later on that you are going to be working on. I'm going to be using it for this video. Now, 1 and 2 in this expression, just labels referring to the first and second experiment that you're choosing among the data that you're given. Now, remember, M is the partial order of reaction with respect to the component A. X of I is the actual component, well, the concentration of that one component in each of the experiments. R's of I is going to be the initial rate of reactions for each of those experiments that you are choosing. Okay, let's do it. If we want to find out the partial rate order of A, what we want to do is to look at experiments in which both B and C are kept constant. We change A, and then we see how that change in A is affecting the initial rate. If you look at experiments 1 and 2, that's exactly what is happening. B, C constant, A changing, initial rate changing. So let's write down the expression for the rate law according to experiments 1 and 2. For experiment 1, this is the general expression. I'm just using the label 1 here, referring to the first experiment. I substitute the values numerically according to the data. Now, I do the same for experiment number 2. You can see that it's exactly the same functional form. The only thing that is changing is the label. Now, this is label for experiment number 2. I substitute the values numerically. When I take the ratio between those two, given the concentrations of B and C are constant, then you can cancel them out. The value of K also gets canceled out. So this expression gets reduced to, in the left-hand side, a number, in the right-hand side, an expression that contains alpha. So I can solve for alpha using the log-log equation. Now, this is telling me that the partial rate order of reaction with respect to A is second order, or that the relationship between the rate and the concentration of A is quadratic. So this is a suggestion. Write down the rate law up to what you know now. So this quadratic relationship here is going to help me to solve the problem as we're going to see now. The next step is to find out the values of beta, gamma, and the rate constant. Now the question is, if I look at the data, are there any other two experiments that keep fixed two concentrations and change only one? Well, let's look at, for example, experiments 3 and 4. You can see for experiments 3 and 4, all A, B, and C are changing, so the initial rate is changing, but we don't really know where that change is coming from because the 3 are changing at the same time. Let's take another set of experiments, 2 and 3. Same idea. If you look at this, all 3 are changing in concentration, so the change in the initial rate, it's changing obviously, but hard to tell where that change is coming from. So if you look at any other combination, you're going to say that, no, it's true that there's no pairs of experiments that will help me figure it out by keeping two of them constant. But one thing that I know is that this quadratic relationship with respect to A. So at the end, I don't really have to care much about A because I can treat it numerically. I just substitute the value of the concentration, I square it, and then I get a number. So let's see how actually that works. If you want to know the partial rate order of B, I have to keep at least the concentration of C constant, because remember, I know how to deal with A. So let's do experiments 2 and 4. I keep the concentration constant. A and B, both are changing. So the initial rate is changing, but I know how much is coming from A because it's a quadratic relationship. So let's do that. Experiments 2 and 4. I write down the rate law using the labels for experiment 2. Numerical substitutions, I get that one expression. For experiment 4, same idea. Numerical substitution, this expression. Now I take the ratio between those two, and I see that the only things that I can cancel are the concentrations of C and the rate constant. Everything else, especially A, I cannot cancel, but this one thing is just going to be a number. So when I reorder the equation, left-hand side, I have a number. Right-hand side, I have an expression that contains beta. When I solve that using the log formula, the value of beta ends up being 0. What does that mean? That means that the concentration of B doesn't have any effect on the rate. So it's 0 order with respect to B. Okay, now the rate is independent of the concentration of B, is quadratic with respect to A. Now I only need to solve for gamma to find out what the partial rate order with respect to C is in my reaction. Now again, I'm going to do something similar to what I did before because I know how to deal with A. I know that B doesn't affect the rate. Now if I want to find out the partial rate order of C, I need a set of experiments that change the concentration of C so I can see the effect of that change in the initial rate. Now if you look at the column for concentrations of C, constant in experiments 1, 2, and 4, the only one that is changing is experiment 3. So I can take any of those combinations using experiment 3. So let's take 2 and 3. The concentration C is changing, concentration of B is changing, but I don't care, it's independent. And then I know what the contribution of the concentration of A is to the change of the initial rate. Okay, let's take experiments 2 and 3. That one makes C change. I take the ratio just as I did before. I write down the expressions, and I'm going to solve for gamma using the log equation. So now when I do this log equation with all the right numerical substitutions, the value of gamma is equal to 1. Now this is telling me the partial rate order of the reaction with respect to C is 1. The rate is linear relationship with the concentration of C. Now I can write down the rate law as I know it now. The only thing that is left out is calculate the value of the rate constant. Now for this one, looking at the data, I can substitute all the appropriate values for any of the experiments, but let's use actually experiment 1. When I do that, I take into account, according to this expression, the initial rate, the concentration of A, and the concentration of C. When I do those substitutions, those numerical substitutions in here, what I find out solving for K is that the value for the rate constant is going to be 0.326 1 over molar squared times second. Now also remember to work out the units, okay? Do not forget to do the dimension analysis to get the units of this rate constant. Now, I mentioned that you can use any of the 4 experiments, so I'm going to ask you also to try with the data from experiment 3. You should get the same value within significant figures. Okay, now we have all the elements, K, and partial rate orders alpha, beta, gamma. In summary, we determined the rate law for a hypothetical reaction using the method of initial rates, for which we did experiments changing the initial concentrations of my reactants and measure the initial rates, how the initial rates change accordingly. We found that under these experimental conditions, with the data given, the rate law could be written in this form. We determined the numerical value for the rate constant, and we found out that the rate order with respect to A was second order, with respect to B was 0 order, and with respect to component C was first order. Now, all the other problems will be done in a similar fashion. You just have to pay attention to the details of this specific problem. I'm going to ask you that for all the other problems that you're practicing, you use the log equation because it's the most general way to solve this problem. But if you have any questions about this one or any of the problems that you find in your book, please let me know. I will be happy to discuss with you, and I will see you around.